Solving applied problems modeled by rational functions. Our objective, we want to use algebra and the graph to solve applied problems that are modeled by rational functions. So let's do a quick recall on what we already know that we're going to make use of here. We know what a rational function is. It is a quotient of two polynomial functions. And we want to recall that when we're dealing with division, quotient, the denominator cannot be equal to 0. In fact, a 0 or zeros in the denominator represents a number that is not in the domain and is a vertical asymptote in the graph. And the third thing we know here, a horizontal asymptote guides what happens at the far right of the graph. And because we're talking about application problems, we're not going to deal with the negative x's, we're going to deal with positive x's. So that is when the values of x are really, really large. Okay, and here we have it again. Application problems deal with positive x situations. Okay, let's remind ourselves what we can find from algebra and/or the graph. When working with applied problems modeled by rational functions, we can solve for y algebraically. We can solve for x graphically. We can find and interpret vertical asymptotes. We can find and interpret horizontal asymptotes. Whoops, that should be an S right there. Sorry about that. We can find and interpret intercepts. And we can find and interpret relevant minimums and maximums in the graph. Little dips or hills in the graph. Okay, let's start off and get a couple of problems under our... Let's do some problems and take a look at let's take a look at a variety of examples. Example 1. The average cost per set for the production of a certain brand of TV set is given by the function c of x is 1,000 plus 30 times x plus 0.1 x squared over x, where x is the number of units produced. Okay, algebraically determine the average cost per set when 30 TV sets are produced, okay? So what is the cost when 30 sets are produced? It is 1,000 plus 30 times 30 plus 0.1, excuse me here, 0.1 times 30 squared, all of this divided by 30. And again, I use parentheses to replace my x's, and then I put the number inside the parentheses. Throw this into a calculator, and the average cost per set when 30 TV sets are produced is $66.33. Okay, for what number of TV sets is the average cost $100? So we want to solve this equation. 100, the average cost, right here. Okay, the average cost is equal to 1,000 plus 30 times x plus 0.1 x squared divided by x. I want to solve for what number of TV sets? So let's do the intersection graphical method here. Move this out of the way, pull up my graph. Let's get that graph in here. Okay, and this is y equals, I get a fraction, 1,000 plus 30 times x plus 0.1 times x squared, all divided by x. And there's the graph of my rational function right there. And we're mostly interested in positive values of x, so we'll kind of go like that. And we want to know what the second equation is y equals 100. We want to solve for x. And so we can see right there, okay, the number of sets, the average cost of 100 is the result of 14.59 TV sets which I would imagine because we haven't gotten to the 15th TV set, that means we have 14 TV sets. So we use the intersection method. Okay, and we came up with x equals 14.59 TV sets. And since there's no such thing as a 0.59 TV set, I'll bet this means that this would be 14 TV sets. We got to round. We can't round up. We've only produced 14.59 of them. Okay, letter C. According to the graph, for what number of TV sets does the average cost reach a minimum, and what is that minimum? Okay, well, let's go to the graph. And we can take out this y equals 100 line, and we're here. And again, we're talking about an application problem. So negative TV sets aren't anything we're worried about. We're concerned about positive TV sets. And you can see here that the graph has come down, hits a minimum, and is going back up. And if you just touch the graph someplace, it'll give you an indication of where important points, what are called critical points. Well, that's the minimum. And it looks like for 100 TV sets, the average cost is $50. So what number of TV sets, 100, does the average cost reach a minimum? It reaches a minimum there of $50 per TV set. So we just used a graph for that one. Okay, let's make a note here. Okay, for 100 TV sets, the average cost reaches a minimum of $50. All right, let's continue on. Give me a moment to do some paper switching. I'm going to finish this example 1 with 2 more pieces. Okay, so I copied over the equation for you. Algebraically, determine if this function has a vertical asymptote. If it does, what is it and what does it represent? Okay, the vertical asymptote, as you remember, is zeros in the denominator. Okay? Determine if it has a vertical asymptote. Yes. At x equals 0. Okay. What does that mean? Well, 0 is at x equals 0 is 0 TV sets. Okay, so what that means is we cannot determine. It's a vertical asymptote, so we have no idea the answer. We have no idea the cost because we can't put this into we can't put 0 in here. So we cannot determine the average cost if 0 TV sets or when 0 TV sets are produced. There you go. This is a 0 in the denominator. It results in a vertical asymptote. So we have no idea what the average cost to produce 0 TV sets is going to be. Let's go back and look at that graph. And you can see here, okay, you can see here's 0 TV sets, and the cost of the average cost is just going higher and higher and higher. This is a vertical asymptote, and so it's never going to touch it. So the average, and basically it's saying that the average cost to produce 0 TV sets is an unknown. We have no idea. There is no average cost value for when we produce 0 TV sets. Okay, let's do the last piece here, letter E in this case. And I'll leave the equation up there so we can take a look at it if we need it. Algebraically determine if this function has a horizontal asymptote. If it does, what is it and what does it represent? Okay, well, looking up here, we need to rewrite this one in its general form, which means this needs to go first. It's the highest degree, followed by this and then that. So 0.1x squared plus 30x plus 1,000. The denominator is just x. And to find horizontal asymptotes, we focus on the leading terms. We're focused on those two. Okay, so we have 0.1x squared divided by x. I'm going to expand the numerator. It's 0.1 times x divided by x. Well, there's a common factor there. And so I'm left with 0.1 times x over 1. X is going to go to infinity, which means the numerator will go to infinity. And so we wind up with infinity over 1, which is infinity. And so we have no horizontal asymptote. There's no y equals infinity, so we have no horizontal asymptote. And again, if we look at our graph, okay, if we look at it here, and I'll pull it back into the center. Let's see if I can get it in here so I can, I'll just kind of zoom out. There you go. You cannot see a horizontal line that is shaping the graph. There's kind of a slanted line, but that is not a horizontal line. All right, let's move on to a second example. I got 3 for you, so we can kind of see a variety of word problems. All right. Example of application problems, excuse me. Example number 2. The percent P of a particulate pollution that can be removed from the smokestacks of an industrial plant by spending C dollars is given by. Okay, 100 times C divided by 8,300 plus C. So the idea is we'll spend money, and what percent of the pollution will we be able to remove? My guess is the more money you spend, the higher the percent of the pollution you'll be able to remove. I'm not sure, that kind of makes sense to me. Okay, the x-intercept and the y-intercept are both the same at 0. Interpret what this means in the context of the problem. Okay, 0, 0. Well, this 0 is C, and this is dollars spent. This 0 is the y variable, that's P, and this is percent removed. Okay, so what does that mean? If I spend no money, if $0 are spent, 0% of particulates are removed. Whoops, I forgot the R in this word. Are removed. And that makes sense. Don't spend any money. I'm not going to remove any of the particulates. Let's just see this graph, by the way. Okay, let's go back and take a look at this and the fact that it crosses at the origin. I'll get rid of that one. I'll change this to the home. Let's see here. This is a y equals, and the numerator is 100 times x, and the denominator is 8,300 plus x. And so there it is. Let's see if I've got anything here that can further help me with what's going on. Oh wow, I had to really zoom out, and we can see what's happening here. Okay, so again, we're not going to spend negative money, so we're not over on this side of the graph. Remember, the x-axis is the money we're going to spend. Okay, so we're not going to spend negative money, no such thing. But you can see with the origin, there's my 0, 0. If I spend $0, I will remove 0% of the particulate pollution. Now notice, if you will, and this looks like it kind of makes sense, as I spend money, the percent I remove goes up pretty quickly, and then it starts to kind of, it continues to rise, but it's not rising quite so fast as we spend money. So let's see what else that might mean for this problem as we answer a couple of more questions. Okay, let me make sure I see the I see the equation up there, right up here. Letter B, algebraically determine if this function has a vertical asymptote. If so, what is it and what does it represent? Okay, well, a vertical asymptote, we focus on the denominator for vertical asymptotes. And let's see, 8,300 plus C, when is that equal to 0? Well, I'll subtract 8,300 from both sides. And it equals 0 when C is equal to 8,300. Okay, this is my vertical asymptote. All right, so we have a vertical asymptote. If so, what is it? It's C equals, or it's a vertical, X equals, if you want to use the XY, C equals negative 8,300. Okay, what does it represent? It says if negative $8,300 is spent, I hope you're already recognizing this makes no sense, the percent of particulate pollution that can be that removed cannot be determined. It's a vertical asymptote. I can't determine the Y value. Okay, give me a second here. I got to do something real quick. Okay, there we go. I can't determine the Y value. Okay, so if I spend this amount of money, the percent of particulate pollution removed cannot be determined. Okay, is it relevant? Nope. Why? Because I'm not gonna. There's no spending of negative money, so it's not relevant. Let's see it in the graph. Okay, we know in the graph it's over here. Okay, and we can see it as we can see it right there. There's my vertical asymptote. And notice how much I've zoomed out on my x-axis. And we said the vertical asymptote was y equals negative 83, x equals, not y equals, x equals. It's a vertical asymptote. Negative 8,300, and there you can see it fitting right in there beautifully. But again, it's an application problem. This half the graph has no meaning because we're spending negative dollars and there's no such thing as spending negative dollars. Okay, let's go to the last one. All right, can 100% of the pollution be removed? Explain why or why not. Well, back up here, can we set this equal to 100? Okay, well, can we do that? All right. So P equals 100. Well, as it turns out, as we look at this, let's take a look. So P equals 100. This is a horizontal line. Is it a horizontal asymptote? Whoops, I'm sorry about that. P equals 100 is a horizontal line. Is it a horizontal asymptote? Well, let's go up to here. Remember, we need to have numerator and denominator in general form. So I'm going to write the C first before I look at my fraction. So 100 over times C in the numerator, C plus 8,300 in the denominator. Now I'm going to look at my leading terms. Okay, my leading term is 100 times C over C, common factor. So we have here, this is 100 over 1, which means P equals 100 is a horizontal asymptote. So the graph is going to approach 100 but never touch it. Okay? So explain why 100% can never be removed. It's a horizontal asymptote. Okay. Tells us that you can get closer and closer to removing 100%, but you'll never remove all 100% all of the pollution, because we have a horizontal asymptote at 100. We're never going to do it. Let's take a look at that on the graph. Okay, it appeared that our graph, okay, let's get out of here. Let's go back to here, y equals 100. Okay, so we're over here, and it appeared like our graph was going to keep going. As we looked at the first part, it was going to keep rising and rising. But it looks like it does, but it has a horizontal asymptote at 100. Notice the little space. It's getting closer and closer. We're up to spending $400,000 here. So what this is telling us is you can keep on spending and spending and spending. You are never going to remove precisely 100%. You may remove 99.999%, but you will never remove 100% because of the horizontal asymptote. Okay, last example. Let me get my papers together one last time. Okay, there we are. Example number 3 here. Suppose the number of employees of a startup company is given by the equation or the function n equals 30 plus 40t divided by, wait a second here, what do I, oh, okay, never mind. N equals 30 plus 40t over 5 plus 2t, where t is the number of months after the company is organized. Okay, so algebraically determine how many employees the company had when it was organized. Well, when it was organized, that means t is 0, because t is the number of months after it was organized. Okay, so n equals 30 plus 40 times 0 divided by 5 plus 2 times 0, and that's going to be 6. So they had 6 employees when it was organized. When did the company reach 10 employees? Okay, we want to have the number of employees to be 10, and we want 10 to equal 30 plus 40t over 5 plus 2t. Well, we'll use the intersection method. Y equals and y equals. And we'll go into the graph and get my iPad in landscape mode. And we'll go in, oops, I should have just started there. Y equals, so we have y equals, and we'll do left side, right side. 30 plus 40x over 5 plus 2x, and then we'll do right side, left side with y equals, okay, something's not quite right. Let's see here, maybe, no, that's just me. Y equals 10. Now I need to recognize that, oh my goodness, where our graph is way up in the 100,000. So I'm going to press the home button. There we go. And I can focus a bit better here when it's not quite so squished. Okay, again, we're not concerned about this side. This is negative time negative time. Not going to be negative time, so I'm being positive time. And when does it hit 10 employees? It looks like after the first month, it hits 10 employees right there. At month 1, we have 10 employees. Okay. Go back to here. So the graph tells us after 1 month. Okay, algebraically determine if this function has a vertical asymptote. I wanted to show this part up here and read this part down here. If so, what is it and what does it represent? Is it relevant in this situation? Okay, vertical asymptote has to do with the denominator, of course, when the denominator is 0. So let's check my denominator. 5 plus 2t, when does it equal 0? Let's subtract 5 from both sides. 2t is negative 5. Let's divide both sides by 2. And t is equal to negative 5 halves. Well, that's the same thing as negative 2.5. And so when the time is negative 2. Whoops, I keep forgetting to do that. Sorry about that, folks. Subtract 5 from both sides. Divide both sides by 2. And I get t is negative 5 halves, which as a decimal is negative 2.5. So when the time is negative 2.5 months, which is not applicable in this problem, we have a vertical asymptote. Vertical asymptote at t equals negative 5 halves. Okay, what is it? What does it represent? Okay, well, it represents that at negative 2.5 months, so 2.5 months before it was even organized, we cannot calculate the number of employees. Well, no, duh. It's 2.5 months before you even put it together. So you certainly cannot calculate the number of employees 2.5 months before things even started. Okay, so is it relevant? No. So the number of employees cannot be determined 2.5 months before organization. If I can get organization in there. I-O-N, kinda. Is it relevant? Nope. It's not relevant. We're not concerned about time before we even thought about it or put it together. We're concerned about when we put it together and then what happened from that point forward. Okay, letter D. Algebraically determine if this function has a horizontal asymptote. If so, what is it and what does it represent? Okay, let's go up to here. Notice that these have the t following the constant in both the numerator and the denominator. Let's write them with the t's first so we can find the leading term. So go down here and I'll write the numerator as 40t plus 30 and write the denominator as 2t plus 5. Now I'm going to focus right here. Okay. Whoops, let me get you focused. There we go, that's better. Okay, that tells us we have 40 times t over 2 times t. If we simplify, the t's are common factors. I can divide numerator and denominator by 20. And so I have 20 over 1. So I do have a horizontal asymptote. It's at y equals 20. Okay, let's take a look at that on the graph before we answer the rest of the question. Okay, here's my graph. Okay, I'll go back to here. And I want to have y equals 20. And you can already see it here because here's 20. And you can see the graph getting closer and closer and closer to 20 as it goes to the right. So y equals 20. There it is. There's my horizontal asymptote. As I go to the right, I'm getting closer and closer. I will never touch it, however, okay, because it's an asymptote. So what does it mean? If so, what is it? Well, the horizontal asymptote is y equals 20. And what does it represent? Well, it represents the number of employees will approach but never touch 20. That's kind of a strange thing to say. Obviously you're going to go from 19 employees to 20 employees, but mathematically using this model, the number of employees will stop at 19. It'll never be 20 in this case, but that's the mathematical piece and how the mathematics turns out when you work with it. So there you have it, a variety of application problems. Remember, we're focused on the positive half of the graph as we look for our solutions.